we're kind of building towards a crescendo, and today's the crescendo, which means today's the day we hopefully make some sense out of a lot of what we talked about in the last 7 weeks. This is the 8th week. And I will, for one purpose or another, kind of anyway, give just a short review. But basically, well, let me just go through this. Basically, one of the things that we have been saying, we started out with, that it takes a watchmaker to make a watch and a camera maker to make a camera. So we infer from that that there are some other things that take a maker. All right, some of the things we talked about over the last several weeks are the human eye, the bacterial flagellum motor, the transport system in something called the kinesin. All right, these are all things that are tiny, tiny, tiny. Well, these two, with a bunch of other ones, are tiny, tiny, tiny inside the cells of our body. And of course, the eye is the one we talked about the first week. We also talked about symbiotic relationships and how they can't. It is hard to see how they could evolve over time. We had one lesson on a scientist giving his explanation as a counter to intelligent design on things that are complex and they need this piece needs this piece needs this piece all at the same time. I know you were here for that, and it was rather silly to listen to the explanations. You can find that one online also. We also talked about things like the tides and the stabilizations of the earth, like with Jupiter being almost like a protector. Jupiter almost being like a protector of the earth. It catches asteroids so they don't crash into it. The moon, if it was a different distance, wouldn't cause the tides. All these things, whether they are celestial, whether they're physical things in the universe, whether they're relationships between species, or whether they're subunits very, very tiny within our body, they all have to be there to sustain this life. And then last week we talked somewhat about the odds of some of these things happening. All right. In other words, we talked a little bit about statistics and probabilities, how they work, and then made some comparisons and showed a couple of videos on the fact that you can't just say that the odds of the eye is such and such, because a evolutionary person will come back and say, well, this could happen to get it. And we saw a video that showed that that's really kind of a dumb thing to speak of it that way. At least I think it is. But that you have to start multiplying these probabilities together. So you take this thing happened, and then this thing happened, and then this thing happened, and this thing happened. You can't treat them as independent events. And by the time you take all of those events and you start multiplying together, the numbers are so astronomically large, it's like, how can they even think that this could happen by accident? All right? The last thing that we had gotten into, or one of the things we had gotten into, we'd gotten into the human cell, where this is what Darwin thought the cell looked like. This is what they know the cell looks like today. And I just read an article just recently, and I brushed over it again today, but it's just so much information that I can't always give you every single thing that comes up. But there's a brand new piece of this puzzle that they just discovered. I don't know if it's this year or last year, but it's really new. And they call it an obelisk, and they don't even know what the function is or why it's there, but they know that it's necessary for life, and it's showing up in places all over the world in different kind of formats inside the human body. At some point or another, I think you got to cry out and go, hey, this had to be designed, all right? Which has been the point so far that I've been trying to make, at least. So, the evidence of the existence of these relationships all point towards an intelligent. But another important piece of the evidence is found in answering this question. This is what we're going to kind of talk about today. What is it that directs, should be an S, and controls each of these integrated systems? Now, the integrated system, scientists use that term, but we said that's the same thing as irreducible complex things. What's an example of an irreducible complex thing in physical?
An engine.
I can't hear you.
An engine.
An engine, yeah, because every part needs to be there, the engine doesn't function. The mousetrap was the simplest one we talked about. But that many of these things, I mean, this has parts just like a rotary motor does, and they all have to be there. And it's inside the cell, so it's even smaller than the human cell. It's so microscopic, they can't even take a picture of it, but they know how it works and that it's there. Same thing with the Kinesin motor and all the other things that we talked about, okay? So these integrated systems show us on the surface that things would have been difficult to produce unless they happen simultaneously. Evolution of those things is very difficult, okay? I don't even think it's possible, and I don't think it happened that way, but they don't even admit that it's hard, okay? But the next step in this, I think, is what is it that guides these things? And to do that, I want to speak just a few minutes today about things, about the kinds of codes that drive things that we're familiar with every day. And then make a comparison to what I'm talking about in the biology of a person or an animal or a plant, etc. So, what I'm going to talk about wasn't true so much just before I was born, back in the 1940s, 50s, 60s. Most everything was mechanical, but as the 70s, 80s, 90s came through and on up to today, a lot more things changed from being purely mechanical to being digitally driven. And you guys live in a digital world nowadays, okay? What's a digital, what do I mean by digital information? Anybody have a clue at all?
Digital information is being like the internet.
The internet runs on digital information. Anything else that you can think of that runs on digital information? Yeah.
Coded information?
It is coded information, but what are some things that run on coded or digital information? I'll give you a short list. And I mean, this is really short. Okay? Now, I'm not talking about the coffee pot that you put on the campfire and you like let it purr. I'm talking about the one that you set there and you press buttons. The microwave, all right? The washing machine, the automobile, your cell phones, your watches nowadays, digital watches, not the ones with hands that sweep and you have to.
Like Apple watches.
Like an Apple Watch, or there's a lot of different brands, absolutely. Alexa, editing, digital art, your digital picture frames, cars, airplanes, all right? All that stuff runs on digital information. So you can have an airplane there nowadays, but that airplane won't fly unless it has some kind of digital information telling it what to do, all right? Your coffee maker, unless you got the old style, it won't work, even though it's got all the integrated parts in it ready to go. Unless it's got a computer program of some kind inside of it, it can't run. Who wrote that code? How is that code written? Because I think there's a profound thing that we can get out of that as to how our bodies compare to that. Our bodies may be able to evolve, I don't think so, evolve from slime into here, but something has to tell all those little teeny parts in the inside what to do. And they know what that is now. They didn't know that until my lifetime. But they know that now. We'll get to what that is in a second. So we want to do two things today. We want to remember that information is not randomly generated. You don't just randomly generate a book, give it a bunch of letters, and then, okay, there's a book. All right? And there is only one source that we know of. Everybody, I don't care how much of a scientist he is, there's only one source we know of that can generate usable information, and that is a mind. A mind had to cause that right there. That's a simple program, the first program that I would have taught to people learning basic computer programming in high school years ago. All right, very simple one. This one simply has the middle line, line 20, that says print hello Wikipedia, and you can see that it did that 10 times. And the reason why it did that was line 10 says, as the variable x goes from 1 to 10, print this, and then the line 30 is the counter, sends it back until that goes from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So when you type run, prints it once, go back to the beginning, prints it twice, go back to the beginning until it gets done 10 times. That didn't happen by accident. It's a simple program, but somebody had to write that. All right? What about something like, that's a really, 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 really teeny tiny segment of the kind of programming that goes on for running a factory, flying an airplane, using your coffee maker. Okay? There's code there. I used to teach that programming. I'm not an expert in it, but I know it's there, and I know it's important. Okay. So, when information goes through a microprocessor, and we're not going to get too technical, I just want to show you a couple of things so we can make an analogy is all. Let's say 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8. Let's say we got an 8-bit register, 8-bit chip. We can have a wire coming in and a wire going out for each one of those 8 registers, right? This one goes in, this one goes out. Each one of these individual circuits can either be a 0 or a 1. You've heard of that before, right? Computers are based on zeros and ones. Well, these zeros and ones aren't really zeros and ones. They're just a way for us to designate whether this is either an on electrical circuit or an off electrical circuit. So when it is on, it's understood to be a 1. If it's turned off, it's understood to be a 0. So right now, this is a 1. This is a 0. This is a 1. This is a 0. Understand? Each one of these at any given instant can be either an on or an off. It can either be a 1 or a 0. So, if I type the capital letter A on my keyboard, it translates that into a off, on, off, 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 on. That's how your computer understands the capital letter A. Okay? We're going to get into this a little bit more. So there's the capital letter A. Electricity can only be on, which is a 1, or it can be off. There's only 2 states of electricity, on and off. So this is it, off, on, off, 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 on, capital letter A. How does the computer see that, or how does that work in the computer? We type the letter A. It goes into the computer as that code, and it comes out on the screen as a capital letter A. Now imagine all the letters you're typing. Imagine the information you're receiving through the internet, whether it's on your phone or on a computer with a text or an email. Every bit of it's being sent that way. Okay? There's no letter A coming over the air into here. It's all sent with this digital signal, like this. In the old style computers, you would type a capital letter A, or maybe like a dissertation or a letter or something, and then you could save that information in these 0 and 1 codes on a hard drive. If you got a computer nowadays, your computer probably has a different kind of hard drive now. It's probably a solid state one, but it works the same, all right? But this was a physical one. The only thing that was on here was on and off, 0 and 1 electrical impulses that it saved in tiny, tiny form so that it could be put back into a register. Computer chips like this, transistors and computer chips like this, they're very tiny nowadays, then run through a microprocessor so that you can see it. That's all the kind of stuff that's inside that computer right here, right? And every one of them has a job. Some of them is used as a storage unit. Some of them are used as temporary storage. Some of them are used for processing so that it can translate that letter A into the code that it needs to know how to process it. But this is the older days. These are bigger components. But when it comes to your phone, it does the same thing, only on very, 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 very tiny solid state pieces. Okay, still processes the information in a very similar way. To go one step further here real quick, this is the binary code for all of the capital letters. So we have what's called the ones place, the twos place, the fours place, the 8, 16, 32, 64, and the 128 place. Now, if you know anything about base numbers, and I'm not going to make you learn the mathematics, in a base 10 system like we use when we're counting on our fingers or adding or subtracting, we always use a base 10 system, and the digits go 1, 2, 0 through 9. 10 digits. Always the digits are always one less than the base. So we're in a base 10, 0 through 9. When we're in base 2, the digits go from 0 to 1 less than the base. The base is 2, so we only have a 0 and a 1. That's why they use a 0 and a 1 in a binary system. So this says I have 1 in the ones place, and I've got 1 in the 64's place. How many is that altogether? 65. Guess what the capital letter B is? 0, 1, 0, 0, 0, 0, 1, 0. Or 64 plus 2, 66. These are what's known as ASCII codes. And every character has its own ASCII code. Okay? ASCII code 65 is the capital letter A. ASCII code 66 is the capital letter B. Here is a chart that shows you A, B, C, D. So if you type A, B, C, D in your computer, it would send this, then this, then this, then this. In fact, every alphanumeric character on your computer keyboard, and there's 256 of them all together, whether it's these little symbols, or whether it's the numbers, or whether it's the lowercase letters, etc., every one of them has an ASCII code. But that's not all there is either. There's also color codes in what's called hexadecimal, base 16. All the kinds of information, every single bit of the kinds of information that your computer does, your car does, when it has to start and send signals to the spark plugs in the newfangled way. It's all electronic now. Whether it's an airplane or whether it's your coffee maker, it doesn't matter. They all have some kind of codes that have to be sent so that those functions can take place. The point I'm trying to make is these are complicated, but somebody had to write them. Okay? You can't function. And to make things worse, here's how the computer understands ABC. That's ABC. But they're in a long string. There's no spaces in between. So it has to know, okay, I take the first 8, and then it knows enough to take the next 8, and knows enough to take the next 8. What if a piece was missing? Or a new piece was put in where it wasn't supposed to? That would totally change it, wouldn't it? Do you think that would happen with things like the genetic code in your DNA? That's what we're going to get to here in a second. We're going to watch a couple films. This is how the computer sees what you type and what it sends. They don't see A, B's, and C's. It's like Matrix. You ever watch that movie? Remember the scene towards the end of the first one where he finally, well, let me back up a little bit. When they're still in that little ship, and the two guys are talking, and there's numbers coming across that computer screen, I see a blonde, right? He's looking at this, but he can read that code like a computer can. That's the point of what that scene was. And then later, they're trying to get, what's the main character? Yeah, they're trying to get him to see this way, and towards the end, when he's ready to fight, what does he see? All of a sudden, the people go away, and he sees this, and he understands what's going on behind the scenes. That's what the whole thing's about, all right? This kind of code. Really interesting, but if you don't know that, you might not get all that. So, the question that I want to ask next then is this. I got to figure out where I left off. Give me just a second. Information from a pen doesn't originate the information, does it? You can have a perfectly built pen laying on the table, and it might drip ink, but it's not going to make a book or even a word by accident. You have to have what in order to create the printed page? And there's several things. There's an easy answer that we've already talked about, but there's actually several things that you need. What were you going to say?
A mind.
Okay, a mind for what? Because I'm going to say that there needs to be a mind for several different parts of that process.
To translate, to comprehend.
I don't want all of them. I just want one. And then somebody else is going to have to do the rest of
Sorry.
it. Okay?
To translate.
Yeah.
Simply to know how to write.
To know how to write, use the pen. To, what was the first one you said?
Translate.
To make the translation. How do we know what the word beginning means? Somebody had to be there before to put that word beginning there, not just to write it down, but to put meaning to it. And then on the other end of it, there has to be somebody there that understands that this was written by a mind, not by an accident. It was written, and I understand the word beginning because there's a presupposed dictionary of words that tells me what that means. And that's true of words. That's true of this. Those ASCII codes were invented by somebody. The computer was taught how to interpret those. And then when we look at the stuff that's coming out of it, we know what we need to understand to know what that information means, even if we don't know what's this part. How many in here already knew this? Kind
Bits
of.
and pieces.
But for the most part, nobody does in here, right? The only reason I do is I taught it and I have a degree in it. Okay? But you don't need to know that in order to look at your phone and read the message. And the same thing is true with biological systems. Okay? Somebody has to have made the object, somebody has to have written the code, the object has to know how to interpret that code, and then the action can be taken out and done. All right? It's a very complex thing, extremely complex. And look at here. What's the permutations on the word cat? All right, which means what are those three letters? How many different ways can you arrange it? Well, there's the 6 different ways you can interpret it. So when we get to something like, I'm going to skip a little bit of this. When we get to something like the DNA, it's not in base 10, but it's not in base 2 either. It's very similar to base 4. 1, 2, 3, 4. There's 4 elements that repeat themselves in various combinations throughout the long string of the DNA. And how those are arranged, how those are written and rewritten through the RNA, and how those things are folded on themselves so that they are able to communicate with each other, causes your body functions through the cells to be able to take place. Who wrote that code? Who knew how to make the cell interpret that code? Coded information is, I think, one of the most powerful evidences that this didn't happen by accident. DNA runs on coded information. It holds more information than all the books in the Library of Congress in stranded DNA. And if we look at that from a scientific notation standpoint, it is so astronomically high as to the improbability of that happening by accident. You remember last week, a couple of you that were here or watched it, that we talked about a guy named Emile Borel, who was a very famous mathematician. He did a lot of statistics, and he wrote a theorem basically that says that if the odds of something happening that are greater than 1 in 10 raised to the 50th power, then that is an event that we can be assured of that will never happen. These kinds of odds are way beyond that. They're in the 10 to the 1,000, 10 to the 2,000 or beyond. And we talked briefly last week about the symposium that went on in 1966, where basically, in a nutshell, the math guys told the biology guys, your theorem don't work, the odds are against it. They didn't listen. They don't care. All right. We've got 15 minutes to watch 13 minutes worth of videos. I got 3. First ones are 2 minutes each, and the last one's 10. All right? And all 3 of them are going to deal a little bit with this problem in one way or another. All right? You ready? Turn this up. I've said this before, I'm going to say it again, I'll probably say it more after this. I am not a scientist. I taught physics before a little bit, and I've taken some science. I'm a math guy, all right? I'm not super smart in math, but I have a math degree and I have a computer degree, all right? But I don't think you need to be a science guy to look through some of this stuff and see the holes. That's my point. I don't think you have to be that. I think, in fact, sometimes if you have the inkling to think a certain direction, no matter what it is you find, you're going to still think in that direction, right? But as I look at this stuff, I do not see that it is likely that the kinds of things that they're up against happen by accident. This first one is simply a little short video on how the DNA works a little bit. All right, something we already talked about. And then we're going to get into a little more technical.
In the body.
Oops.
There are 4 main macromolecules in the body: carbohydrates, proteins, lipids, and nucleic acids. These first 3 will be discussed in other videos, but this video will focus on nucleic acids, specifically DNA and RNA. As you may have heard, DNA is the chemical blueprint for our body. Using just 4 different subunits in adenine, guanine, cytosine, and thymine, it codes for the over 100,000 different proteins in the body. To understand how this is done, let's take a look at a different coding system, the English alphabet. In the way that an old, fragile book might be housed in a library, DNA is kept locked up in the nuclei of cells. To prevent damage to such an old book, people read copies of it. Analogously, slightly different copies of DNA, called RNA, are formed and exported from the nucleus for reading. The book only contains the 26 letters of the English alphabet, and DNA only has the 4 subunits, or nitrogenous bases, described earlier. If we put letters together, we can form a word, but the word itself doesn't have meaning. It takes someone who speaks English to read the word and interpret it. In RNA, a set of 3 adjacent bases is called a codon. The codon itself doesn't have a meaning until a tRNA molecule reads it and matches it up with a protein subunit, or amino acid. Once we have words, we can put them together to make a functional sentence. In an analogous manner, adjacent codons make up a gene, and the corresponding amino acids are put together to make a protein. This protein then folds up and performs actions based on its reactivity. DNA and RNA even have start and stop codons on either side of the gene, the same way we use capital letters and punctuation to start and stop a sentence. But imagine if someone came in and changed, added, or erased a letter. Depending on the change, the sentence may still make perfect sense, some sense, or it might be completely nonsensical. In the same way, a mutation in DNA can result in a protein that is either still functional, partially functional, or completely dysfunctional. If the protein is fairly unimportant, a mutation may not cause any disease. If the protein is vital, a mutation can cause a severe disease.
So the video we're going to watch at the end, it's 10 minutes long, is going to deal with the mutation end of it and why, when those codes change, it doesn't do what evolutionary scientists say it does. So I'm going to save that for a minute here. But notice how they are. This is not coming from a creationist. This is coming from somebody that would believe in evolution and believe in random chances and that sort of thing. They're giving you a very simple example that looks like with the word cat. Well, it could possibly make sense if you change one letter. But what if that string was longer than 3, like we've been talking about? What if that string is 5,000 words long, or millions of letters long, like the Library of Congress, which is what can be crammed into a DNA? You get some of those wrong, and there's big changes. So they're making it, as far as I'm concerned, overly simplistic, so you can go, oh yeah, you could spell the cat another way, and the thing would still work. No, that's being deceiving. That's not how it works. Okay? It's not how it works at all. All right, this next one is a guy named Jason Lyle. I listened to a lot of his stuff. This is a short segment, about a 2-minute segment from a lecture he gave that's kind of on this same topic. So,
one line of evidence involves information theory. Information studies how information science, information theory studies how information is transmitted. And there are several laws of information science. Dr. Werner Gitt, who wrote the book In the Beginning Was Information. And he's a really brilliant Christian scholar. But he points out that whenever information is transmitted, you never gain information in the process of transmission. And when you follow information backwards along the chain of transmission events, it always leads to a mental source, the mind of the sender. Information always comes from the mind, ultimately. Now, inanimate machines can copy information and replicate it and so on, but they can't create brand new creative information. Can't do it. Computers can copy it, transmit it, they can't make it. Minds create information. And that's very interesting because, of course, in DNA, what do we have? Information. The instructions to make you coded on a molecule. Amazing, really. And where did you get your informations in your DNA? You got it from your parents, they got it from their parents. It's been copied many times. But ultimately, it has to go back to a mind, according to the laws of information science. And that, of course, is exactly what we expect, given what the Bible says about creation. This idea that mutations accumulate in DNA and gradually add information, that's contrary to the laws of science. It's contrary to the law of information transmission. Mutations might convey survival value under certain circumstances. That does happen. But they don't increase information. Dr. Lee Spetner, one of the world's experts on mutations, says all point mutations that have been studied on a molecular level turn out to reduce the genetic information, not to increase it. And in some rare instances, that loss can actually help you survive. But in any case, it doesn't help. It can't be responsible for the information we have in our DNA. He says not even one mutation has been observed that has full information in the genome. Isn't that interesting? And so when we study genetics and information science, we find it confirms Genesis creation. It's inconsistent with the idea of evolution. Millions of years of random processes generating the information in our DNA, not possible according to the laws of science as we understand them.
what was one of the things we said from the very beginning? We said it for several sessions throughout so far. Can we prove beyond a shadow of a doubt that there is a God or that there is even an intelligent being? And the answer is no. You remember that. Good. Okay? The answer is no, we cannot. But they cannot prove that their process is for sure either. All we can do is look at evidence. And for me, looking at the evidence that we have so far, and especially this information evidence, when they're talking about that RNA, DNA interaction and some of the other things that go on in the cell, there's some things that are analogous to this, all right? They're not done the same way, but the information is put in, it's coded, it's done, it's read, okay? That's what these parts of a computer did. And modern versions of them do the same thing. Information comes from a mind. Now, next thing we're going to have on the screen here is another doctor. I forget his name, Don something. They'll say it at the beginning. And this is about a 10-minute excerpt of about an hour or so talk that he did, interview he did. But it talks a lot about the mutations. Mutations are the only mechanism that along with survival of the fittest, there's another word for it, I can't think of it right now. But it is the only mechanism that they have that says that we can change from a cow to a whale, or a monkey to a man, or an amoeba to a fish, all right? All of these things have to be done some way or another, and the mutation is what they rely heavily on. Okay, the mutation they say can change over time, and then eventually you get this set of information instead, so you got a new species, a new creature, or whatever. This next guy says that's not possible.
Mutations are essential for evolution. They're the only means of producing the new features that are required by evolution to change microbes into microbiologists. But are mutations really up for the job? I'm here today with Dr. Don Batten, who has a doctorate in plant biology, and so is well qualified to help us dive into the technical aspects of this big question. So Don, firstly, what are mutations?
Well, mutations are accidental changes in the DNA. So when we have children, we pass on our DNA to our children. Mistakes are made. Some mistakes are made in copying that information. Those mistakes are called mutations. So it's a bit like if you're typing on your computer and you hit the wrong key, you're trying to copy some text and you hit the wrong key, that's a typo. Well, mutations are like typos in our DNA.
Okay, so what do mutations have to do to make evolution work?
Well, if you're going to change a worm into a fish, you have to add the instructions in the DNA to specify how to make features that fish have that microbes don't have, or that worms don't have. So a fish has gills, it has eyes, it has all sorts of features that are absent in the worm. So how do you get the instructions to make all those extra features? That's what mutations have to explain. So if you think about changing a microbe into a microbiologist, the simplest microbe that's going to live, we're talking about DNA information would occupy a book the size of the Bible.
That's a lot of pages.
That's a lot of pages of information.
Yeah.
So to change into a human, though, a human has 1,000 sized books, 1,000 Bible-sized books of information. So you have to add 999 books of new information, which specify how to make all the features that we have that microbes don't have. A lot of the motors we see in living things, the things that make our muscles work, the linear motors and the rotary motors, and these are multiple proteins that have to be the right sequence to function together and to do what they do. So accidents can't create that sort of thing.
So just like the typo you were talking about before, it sounds like mutations are going to wreck things.
Correct. In fact, think about a computer program and you're typing up a computer program. If you add a mistake into the computer program that wrecks it, doesn't create some new structure, some new feature. And that's what we find mutations do. They're wrecking things. In fact, there are over 500,000 mutations identified that cause human disease.
I was going to say, we've got some evidence for this. That sounds like some evidence.
So if you look up the internet, there's a human gene mutation database, and it specifies there's 500,000 so far found mutations that cause human disease. So they're wrecking us, they're not creating us. And that's what they're known for, wrecking things.
Okay, but evolution so far, we're saying it needs mutations for this creative process. How does that work then?
Well, it doesn't. That's the problem. So sometimes mutations can be helpful, but even when they're helpful, they still wreck things.
So, Don, then are you saying that all mutations are harmful?
No, as we just discussed, there are examples of helpful mutations, but even the helpful mutations are breaking things. So it's a bit like the Russians have invaded Ukraine. So Ukraine has blown up bridges to stop the tanks from advancing.
Mm-hmm.
Okay, so it's helpful to blow up the bridges to stop the tanks advancing, but blowing up the bridges doesn't explain how you make the bridges.
Mm.
And so the mutations blow up bridges,
Yes.
which can be helpful,
Yeah.
but they don't create the bridges. That's the problem.
Mm-hmm. But in effect, yeah, evolution is saying they need to.
Yes, the evolution has to have a mechanism for creating new bridges, not just blowing up the ones that are there.
When we're talking about mutations, often people are thinking about cancer. Is that relevant?
Yeah, very much relevant, yes. So cancer is caused by mutation. And my own father died with prostate cancer, so it's a bit close to home. And many of us have been touched by that. So yeah, mutations are killing us, they're not creating us. And this is a fundamental problem. So when mutations were discovered back in the early 1900s, they got quite excited about that, especially when they discovered that radiation can induce mutations, because mutations were then thought, well, there's a mechanism for evolution to create new features. So they embarked on a program of breeding fruit flies after irradiating them. So they irradiated them with gamma rays and
Right.
induced mutations. This is the little ferment flies you get when you leave some fruit out on the bench, and you get the little tiny flies flying. They're Drosophila ferment flies, and they've been used for laboratory experiments for 100 years. And so they irradiated these flies expecting to make pseudoflies. And they did that for many years, and they never got anything other than a defective fly. So they got ones without wings and ones without legs and ones with extra antennae and all sorts of defective flies, but never got pseudoflies.
But they genuinely thought they were going to produce
They
them.
genuinely thought they were going to sort of supply, they were going to prove evolution basically by, breeding these flies with irradiation, mutating them and making them into, demonstrating how evolution progresses.
And what do you think led them to think that the idea of mutations was going to do that?
Well, modern genetics have found that the features of living things are based on our genes. And so you need to find a way of getting new genes to create the new features. So this became well known and became a crisis for evolution. And then they discovered mutations. Oh, this is how they get the new features. And because the mutation is a new feature in a sense, so a fruit fly without wings is different,
Yes.
But you don't put wings on fruit flies by mutation, you just take them off. So you destroy the information, you don't create it. But in every case, you're breaking something, you're not actually making something, and this is what was hoped, that they'd have a mechanism for making things. But mutations don't make things, they break things.
And so do you think, Don, that when people hear that a mutation has changed something, maybe it's beneficial or it's just different, that you sort of automatically think that that means...
Oh, evolution's happening.
Yeah.
That's right, yeah.
Okay.
Yeah, and it's not. People are being misled. Well, probably don't know enough about it to understand that it's actually a downhill change, whereas we need serious uphill change to explain evolution.
And why do we need this serious uphill change?
Well, we go back to our one book of information in the bacterium versus 1,000 books in a human. So all those extra books are for all those extra features that we have that they don't have. So there's no mechanism for creating all that new specific information for all those features. Mutations just don't cut it.
And yet it's hanging on this, in a sense.
True, there's no other mechanism. I don't know of any government-approved high school textbook which acknowledges the limitations of mutations.
Oh.
In fact, most of them don't even mention mutations. They hardly mention them, maybe in one paragraph. They hardly mention mutations. They concentrate on natural selection. So natural selection, they show examples of natural selection, and there are plenty of examples of natural selection. but they actually avoid talking much about mutations because I think they would realise that students will say, hang on a minute, this doesn't add up. How can accidental changes create all these features? Because they're also studying some of the amazing biology in living things in their textbooks, some of the motors and amazing biochemistry and so on. And it just doesn't add up that accidents create all this stuff. So I think they're just avoiding talking about mutations because, well, the game's up for mutations, they don't work. If they talked about mutations and told students the reality, the students would realise that evolution is dead in the water.
All right, so if mutations can't actually make all that new information, where did it come from?
Well, the evidence shouts at us that there's a superior, absolutely intelligent creator who created everything. That's what it's telling us. You don't get sophisticated programming from accidents, from nature. Chemistry doesn't produce programming. Only intelligence produces programming, and living things are full of programs, and they have to have a programmer. And the only programmer that's possible is God, the creator who's revealed in the Bible.
We admit that about all the things we see that people create today that require such planning and ingenuity, but we don't like to admit potentially that we also, the earth, the universe, people, that they've been created with a plan and a purpose in mind.
Absolutely. And we talked about bridges a while ago. Bridges require an engineer to design them. They don't just make themselves. You can destroy bridges easily, but you can't create them easily. And creating a bridge requires a creator.
So, at the very beginning, I said we were going to cover this in two parts. We're still in the first part. We're going to be in the first part for a little bit longer, quite a bit longer possibly. The first part, I don't know if anybody remembers, has to do with the physical things that we find around us and how to explain some of the stuff that science is saying that's happening over long periods of time by accident without a mind. All right? And that's what these first 8 basically dealt with in kind of a sequence. This is the end of that part. One second, I want to make sure you get your question in, but I want to get this out first. So the decision we have to come down to is which way does the evidence fall? I mean, the majority of the world, I don't know if they understand the arguments totally or not, but the majority of the world, whether they're scientific people or not, believe somehow or another that the evolutionary process is what led to all this. You can't even say caused. You can't say created. You can't use that if you're an evolutionist. You can't do that because that implies a mind. The other possibility is that there was a mind behind it. Right? There's debates as to what that mind should be, but there's a mind behind it, and that's the big debate right now. And it goes back to Romans chapter 1. And there's a whole section here we're going to read as time goes on, but I want to read one verse. For his eternal attributes, namely his eternal power and divine nature, have been clearly perceived ever since the beginning of the world in the things that have been made. I think we're supposed to look around at the universe, see these intricate details and the things that happen, and understand I can't do that. The scientists can't do that. That had to come from somebody beyond me. That's what the whole first part of this is about. We're not at the end of it yet, but that's what we're talking about now. The second part of this, okay, if we decide after all this evidence that there's somebody out there besides ourselves that did this, how do we find out who it is? That's when we're going to delve into the Bible and some other religious books to try to make that decision. That's going to be quite a few weeks down the road yet. But that's what we're headed towards, okay? This isn't all going to be, let's kick science in the ribs. This is going to be, now that we know that this is probably not the case, what everybody believes now, and that there was an intelligence, how do we figure out what that intelligence is, and why is the Bible the one that we choose, all right? So that's what this course as a collective is going to be. Yes?
It said that mutations can only destroy and not create, but what about those, like the pig with 2 heads and stuff?
The what?
The pig with like two heads.
Yeah, but that's destroying it.
Yeah, that is a bad one. There's also good examples like Bob London. He's a somewhat famous trick shooter. He had a quick draw and also a reholster in 0.15 seconds, so about as fast as the blink of an eye. And he had an extra sheet of muscle on his hand that allowed him to do that. So that's a random mutation that was actually beneficial.
Even this guy says that there are possibilities. I don't know if you noticed that in there. There are possibilities of mutations making something. In other words, how do they? I'm trying to think of an example I heard of a while back, and this is hopefully going to answer your question. How do they eradicate certain kinds of diseases? Well, they can maybe change that DNA code. Does it make a new human being? Does it make a monkey into a man?
Yeah, this is obviously a lot less complicated than that. It's just an extra sheet of muscle.
But the point is that mutations can do things like that, but what they are trying to do is to take and say, we started out with a cow, how did we get a whale out of that? We started out with a monkey, how do we get a man out of that? We started out with an amoeba, we need another 999 Bible-sized book of coded information to go from there to there. That's what he's refuting. Not the simple things like what you're talking about that he claims even can happen. I don't know if that helps or not. Yes?
well,
No?
it does sort of, because I don't think you can get from a little single-celled organism to a human, but the scientific theory that it is not backed by science because they can't observe it, obviously, is just that those small, tiny, minor changes can eventually lead to something bigger. But obviously that can't be proven. But that was just a tiny example of an extra sheet of muscle in his hand.
Will you watch? You were here last week. Was it last week where we talked about, or was it the week before? Where we talked about oh, I'm trying to remember what it was. Where it had the different levels of the bees and stuff that that was the week before. So not last week, watch the one from the week before. Now it doesn't totally talk about your specific question, but I think it's enough to get you thinking the way that I am. It would take me going through that whole thing again to do it. But basically, they're trying to get a irreducible system. You know, read Michael Beattie. Michael Beattie. He's got a book called Darwin's Black Box, and he goes into this in detail, that these mechanisms are put together in a certain way, and they had to be put together that way from the beginning, or they wouldn't work. Well, this scientist that I have on 2 weeks ago tries to explain that away in a scientific way. And what we find out is, it's really kind of silly. All right? It doesn't mean that some things can't happen, but they're trying to change, like this guy said, a microbe into a microbiologist. All right? And we talked that same week about the difference between macro and microevolution. You know that there's a difference,
Yeah.
right? So microevolution is something that happens all the time. We breed dogs, we get an extra muscle, okay? But what we don't do is cross. In other words, we don't get to Darwin's tree. We see individual lines going up instead. There's a human line, there's a monkey line, there's a whale line, okay? That's what we see. Changing a person, a feature of a person over time, changing one kind of dog into another kind of dog. What was it, a terrier and a bulldog makes a pit bull? That's a microevolutionary thing. Now that new bulldog has different kinds of features than the originals. Same thing could happen with the muscle in the hand, but it still didn't change that man into something new.
Yeah, this sheet of muscle is still just something that humans already have, so it's not anything new being developed. Well, it is something new, but like it's
Well,
not
we don't know that,
something that
that,
already exists.
we don't know that it didn't already exist in some other human in the past either. I mean, I'm not saying
But
it
it
didn't.
happened through random mutation, but like it's also not the same as like an air sac in a lungfish turning into a lung.
Yeah.
That is something that has never been seen as proven or even a reason to believe it has ever happened.
I don't think I disagree with you, okay? And it's a good question, and it's one that is gonna get thrown at you, so I think it's a good one to think about and have an answer for. But I don't think it changes our debate. I don't. Okay? Anybody else? Good question. I don't have every answer. What I have, I think, over the last 60 years of my life, is enough pieces of evidence to make me pretty sure that it didn't happen the way that the Darwinian evolutionist says it happened. That's what I'm looking for.